Heating and cooling curves by Tabitha, Arshum, and Zack. Heating and cooling curves are linear graphs that show how the temperature of a substance changes as it heats up or cools down over time. The x-axis represents time and the y-axis represents temperature, usually given in degrees Celsius. It is important to note that when the graph is a horizontal line, the substance is undergoing a phase change. Looking at the heating curve for water, you can see that the horizontal lines occur at the melting and boiling points of water, where the water changes phase. A cooling curve for water is just the opposite, only here the lines represent condensation and freezing. So why is there no temperature change during phase changes? The reason for this constant temperature has to do with kinetic and potential energy. Kinetic energy is the energy a substance possesses due to motion. Potential energy is the energy a substance possesses due to relative position. Wherever the graph is horizontal, potential energy is increasing, while kinetic energy remains constant. This is because all of the heat energy goes into overcoming the intermolecular forces. This increases the potential energy of the substance as the molecules move farther away from each other, but does not contribute to kinetic energy. However, wherever the slope of the graph is not zero, kinetic energy is changing while potential energy remains constant. The heat energy causes the molecules to speed up, increasing kinetic energy, but their distance from each other remains constant. Now that we understand how the curves work, let's take a look at an example problem. Calculate the energy required to convert 5 grams of ice at negative 20 degrees Celsius to steam at 250 degrees Celsius. And we're given the specific heat of ice, the specific heat of liquid water, and the specific heat of steam, as well as the heat of fusion and the heat of vaporization of water. So in the example, we're given a 5-gram sample of ice at negative 20 degrees Celsius and are told to find the total amount of energy required to produce steam at 250 degrees Celsius. Before the ice can melt, the temperature of the ice must first be raised to its melting point or fusion point. From the graph, it shows the fusion point to be at 0 degrees Celsius. To calculate the energy required to do this, we use the equation Q equals mc delta T and the specific heat of ice. Now that we've reached the heat of fusion, the temperature stays constant as we go through the phase change, so we can no longer use Q equals mc delta T. Instead, we use the heat of fusion in the equation Q equals mass times heat of fusion. We repeat this process for the next phase change, using Q equals mc delta T and the specific heat for liquid water to raise the temperature to 100 degrees Celsius. Then the heat of vaporization can be used in the next phase change. To reach the final temperature of 250 degrees Celsius, we use Q equals mc delta T with the specific heat of steam. Once you've calculated the energy required for each step, we add all of them up to find the total amount of energy required for this process. Understanding heating and cooling curves can be very helpful in problems like this one. This concludes the heating and cooling curves video. Thank you for watching.